Okay, good morning. Welcome to IIT Madras. So how many of you are here for the first time at IIT Madras? Okay, great. So I'll welcome to IIT Madras, and my name is Arun Rajkumar. I'm a faculty here in the uh, computer science department, now in the data science and AI, newly established data science and AI department. What I want to do today is to kind of give a very broad overview of machine learning, AI, and things like that that you might have heard these buzzwords, and just to, I mean, this is not like a teaching session, but more like a introductory session where, just to introduce you to certain ideas and just tell you why these are interesting things and why you should be interested in it in these times. So we'll get started. So let us make this as interactive as possible. So if you have any questions at any point, do let me know, both the students and the parents, relevant to what we are talking now. So we'll anyway have a final interaction session where we can ask any questions also. Okay, so let's start with the basic questions. Why should we care about learning? Why should we care about machine learning, artificial intelligence? Why are we even talking about that? Why is there such a big crowd for this program here, right? And the reasons are many. So here is one way to illustrate this. So what I did recently is I searched for these keywords: machine learning, deep learning, artificial intelligence. So these are keywords, buzzwords that all of you might have heard in different contexts. And I try to understand, the Google trends for these concepts, right? So what you're seeing in this graph is the x-axis is the timeline starting from 2004 till today, and this is like the number of keyword searches in Google, or roughly the volume of keywords that have been searched in Google over this period of time. And as you can see, in the last maybe 10 years or maybe less than that, 5 years or so, there has been like an exponential increase in interest in things like machine learning, data science, AI, and things like that. Why is this? Because we have many more companies that are data intensive these days. Your Facebooks, your Instagrams, and whatnot, or Amazon, Flipkart, all of these crunch massive, terabytes of data on a day-to-day basis, and they want to derive insights from data, right? So, data, as you must have heard also, right? So data is kind of the new oil. If you know how to handle data these days, you kind of have a superpower, right? So that's what people say these days. And this is perhaps for the parents here. Now, if you're wondering why should you put your ward in a data science related course, right? So this is like the top 10 strategic trends listed by Forbes magazine in 2024. And as you can, if you just eyeball this list, you will see a lot of AI related things here, right? So democratized generative AI, trust, risk, security, AI, machine learning, and so on and so forth, right? So I think in the next, 10 years at least, AI is kind of going to revolutionize a lot of industries, and we'll talk a bit about that as well in the coming slides. So there is good reason why we should be interested in knowing this technology and understanding this technology. That is number one. Now, where is AI used, right? So why is fine? So we are all kind of convinced that it's a much hyped thing. So I don't want to hype it any further for you guys. But where is this used? So let's try to understand. So who is this person? Okay, Albert Einstein, but for our purposes, this is, let's assume, some prototypical human being. Well, perhaps not prototypical, but still, let's assume that this is some human being. And we want to understand, how is this AI related to human beings, a prototypical human being? One of the things that AI allows us to do is to understand vision. What do we mean by that? The eye, right? The human eye is a very evolved organ, right? So it has evolved over millions and millions of years. That, if I look at this room, I know that there are chairs here, there are students here, there are parents sitting there, there's a camera there, and so on and so forth, without even really doing anything, right? So I can already process these many things, and my brain knows that this is what is there in this room. Now, we want to make a computer understand this, right? So we want to make a computer simulate our human eye. And that's not an easy thing at all. What comes so easy for humans is very, very complicated thing to get a computer to do that, right? So, and this is one of the things where AI ML helps. And what might be one use of doing this, right? So can somebody think of a use of making a computer simulate the human eye? Let's say we have a computer that can, simulate the human eye. Why would that be a useful thing to do? Any thoughts? Yeah.
Blind people can see.
Blind people can see, sure. So you can so you can think of an AI-based expert system as as a pseudo eye for a blind person. Perhaps yes, yeah. But even for us, right? So where would that be a useful thing? Or in what applications do you think that might be of use? Yeah.
Self-driving cars.
Self-driving cars, excellent, right? So you have a car, nobody wants to drive cars anymore, so we want computers to drive cars, and when the car is driving, why do you think self-driving cars need computer vision?
Because
Sit down. Yeah.
in order to gauge the traffic and avoid accidents on the road,
Yeah.
self-driving cars having computer vision would be a very good thing.
Yeah. So what property of vision does it use? Well, it tries to detect objects, right? So it tries to detect other cars on the road and then tries to navigate it, right? So now if you want to develop a self-driving car, then you have to simulate the human eye, right? So the computer has to simulate the human eye. There is no other way to do that, right? So, and AI ML kind of helps us do these things, right? So I won't say we are there yet. Self-driving cars will never happen in India as far as I mean, our roads and our traffic conditions are very different from the Western conditions, but still at least in the West, people are trying to come up with computer vision based things to simulate self-driving cars. Great. The other thing that we do easily and we are doing now is speech, right? So we can speak, we can understand. We might say the same thing, we might mean the same thing, but we might say it in different ways. And now we want computers to understand speech as well. Right? So speech recognition is an important thing, right? So some of you might have seen Alexas and your Google voices, and so you say, okay, Google, and immediately Google recognizes your voice, right? So how does that happen? Well, there is a system that is built in which is trying to understand human speech, right? So and that is, again, there is a machine learning artificial intelligence system sitting inside this as well. So that is one other example. Text is another thing. So we write a lot of things, emails and so on and so forth. I mean, text has become a natural way to communicate between people. And again, in text also, right? So if there is like a 5-mark question that is being asked in your exam, the way she writes would be much different from the answer that he might give, right? So it might be the same subjective type question. You might mean the same thing, but then, the way that you express things is completely different. The meaning is the same, and now if you want a computer to understand this, right? So for example, if I am Amazon and I want to understand how people perceive my products in terms of reviews, and now I want to understand these reviews, right? So if I am an Amazon, if I have built Amazon, right? So I cannot go through all reviews manually and see if these reviews are good reviews, these reviews are bad reviews, right? So I want a system which can look at these reviews and tell me automatically whether this is saying something good about the product or saying something bad about the product. And we express things in different ways, right? So maybe there is somebody who says, hey, it's a wonderful product, it never works, right? So now we understand that there is some sarcasm involved in it, but now to make a computer understand sarcasm is a very, very challenging thing, right? So now that's a whole different thing, right? So because as humans, we have again evolved to communicate, we have understood how to communicate and so on. So how can you make a computer do that is always a challenge. Again, AI, ML, and things like that help us here as well. Of course, the big holy grail of whole of science, I would say, is to understand the human brain, right? So how does the brain work, right? So man has been interested in understanding this single question ever since time immemorial. We want to understand how the human brain works because we always want to simulate, human beings itself, right? So and that has been a quest, and AI ML is kind of pushing us towards that direction. I won't say we are anywhere close, but because it's not just AI ML that's going to help us, it's going to be neuroscience and so on and so forth that will finally help us hopefully achieve that, but we are far away from that. But these are not the only things, right? So this is like a prototypical human who can do certain things, naturally, but then it's hard for a computer to do, but then we want computer to get these human-like abilities, and AI ML helps us with that. But that's not the only thing, right? So there are several other examples where AI ML might be of use. For example, you might have data from laboratory experiments which you want to analyze and gain some insights. Maybe there is sports, you want to predict, well, the IPL just got over, maybe there is a, and I think the T20, I know how many of you follow cricket, but then I think there is this T20 World Cup that is starting, and you want to predict who will win the T20 World Cup, right? So, and every single match, you may want to, make a prediction as to who would win, and then you again want to crunch a lot of data and figure that out as well. There are so many other examples, and we'll see later as we go along. But then the bigger question, which we want to at least try to understand today, and this is the goal of today's talk, is to understand, well, what really is learning, right? So what really is this buzzwords, machine learning, artificial intelligence, and so on and so forth. But before I tell you that, I want to hear your thoughts. What do you think is machine learning? What do you think is AI? What is your understanding at this point? I'm sure all of you have heard. All of you have heard this term, machine learning, AI, before? Yeah, so what is your understanding of this? What is AI? What is ML? Okay, any thoughts, anybody?
A machine finding trends from its given data.
Machine finding trends from given data. So there is some data, and then you want to figure out some trend from data. Wonderful, that's a valid answer. Any other answers? Yeah.
Artificial intelligence is the ability of machines to perceive and learn and apply knowledge.
Perceive, learn, and apply knowledge. So there are lots of keywords there already, right? So you have to perceive something and then learn from it and then apply it somewhere, right? So we'll try to break these down as we go along. Fair enough, right? So that's the textbook definition as well. Yeah. Anything else? So give me, yeah. It learns from its own mistakes. Wonderful, right? So wish we also did that in life. But yeah, so that is a very important thing that we want computers to do, right? So because you make mistakes and then you learn from it and then you become better and better, right? So absolutely. So that's also possible.
Just like how humans have spent millions of years trying to optimize, trying to better, trying to advance themselves, machines try to optimize themselves, advance themselves, make them much more compact, technical.
Yeah, sure. So there is this whole evolution that has happened so that we are more suited to the environment in which we are currently living, so that we can navigate the world in a efficient way, right? So that has already happened by trial and error over millions and millions of years. Now you want computers to somehow get that ability, right? So that's not at all an easy thing, because this has taken so many millions of years for humans. Why should we even expect computers to do that very quickly, right? So that's the challenge here as well. Anything else before we start thinking about this? Okay, great. So all the answers that you gave are correct. But we need to make it slightly more precise, right? So to really understand what is learning, what is not learning, we have to make this slightly more precise, and let's try to understand that, right? So with some examples. So here is a program. How many of you can code? How many of you have done some coding? Okay, most of you. So how many of you have never written a piece of code in your life? Okay, and why is that?
Not really my thing. I never really got it.
It's not really your thing, but did you have a code
I
thing?
did try to get into Python and something, but not. And I am a commerce student, so not really my thing.
Okay. So we'll see why commerce students should code in a minute. But yeah, so sure. But I understand. So for those who understand, so this is like a pseudo code, and I want you to tell me, what is this pseudo code doing? Can somebody tell me what is happening in this code? So this is a function. It's called something. It takes a number n, let's say, and then returns either false or true based on certain conditions. So what is this? What is this program doing? Just raise your hands if you know what this program is doing. If you have any questions, ask me.
Checking whether the number is a prime number.
It's great. It's checking whether the given number is a prime number or not. And can you explain why that is the case?
Because if a number is divisible by another number, then it's not prime. So we are checking if the remainder is 0.
Okay. So what you are doing is, if n is less than or equal to 1, then we are saying, well, it's false, it's not a prime number. But if otherwise, if n is not less than or equal to 1, which means that it is 2 or above, then we are trying to, go from 2 to n minus 1 and then trying to see If it is divisible by a particular number, if it has found a factor, then yes, then it cannot be a prime number. Wonderful. So is everybody convinced that this program is actually trying to find if a number is prime or not? So let's say I give the input as 10. What would be the output to this? Why is it false? So where will the program return false? At what point? Second last? No, yeah, it's going to return here, second last line, but then at what value of I is it going to return false? 2, right? So because 10 is divisible by 2, so this is false, right? What if I give the input as 23? Okay, why would it return true? Because it will try everything from 2 to 22. None of the values would be divisible by this, and so it will return true. Fine. So just a quick aside. So is this the fastest way to find if a number is prime or not? Is there a faster way? When I mean faster, right? So here for 23, you are checking from 2 to 22, and then figuring out if a number is prime or not. Huh? N by 2. Why is it n by 2?
Like for example, if the number is 20, it is enough if we check till 10. We don't need to check for 11.
Why?
Because we would have already checked for 2. So 2 into 11 will become 22, which is greater than the number we have entered.
Wonderful. So he's saying you don't have to check till n. You can n minus 1. You can check till n by 2. So can you make it faster? With the same logic, but then slightly, can you make it faster? Okay, I'm going to leave that as an exercise for you because that has nothing to do with AI or ML, but think about it. So you can do it much faster than this, but for our purposes, the reason that I brought this up is that, here is an input, I give an input, I have a program, and then the program returns whether true or false, right? So that's what it's going to tell me, right? So this is one world, right? So we'll keep this at the back of your mind. So we'll play a different game now. So don't shout out the answer, but can you guess the next number? If you can, just put your hands up. Okay, 1, 2, 3, 2, 5, 11, 23, 47. What's the next number? Don't tell me. Just keep your hands raised if you can. I'll give you another 30 seconds for people who have not yet figured out. Okay, so what's the answer? 0, 0, 0.
95.
Okay, great, 95. Does everybody agree that it's 95?
Yes.
Okay, why is it 95?
The difference between all the 4 numbers is from 3, 6, 12, 24, and 48.
Okay,
So the difference is multiplied by 2.
the difference is multiplied by 2.
So 12, the last one is 24. 24 into 40, so 47 is 40 is 95.
95. Okay, great. So is there any different reasoning that anybody else has to say why is it 95? What was your reasoning?
So the previous number should be multiplied by 2 plus.
Okay, so it's just similar to what she says. So if you want to find a number, then you look at the previous number, multiply it by 2, and then add 1 to it, right? So that's the goal. Okay, so here is another one. Okay, so if you have figured out, just put your hands up. Okay, for people who did not get this, so this is 2 times 2 plus 1 is 5, 5 times 2 plus 1 is 11, 11 times 2 plus 1 is 23, 23 times 2 plus 1 is 47, 47 times 2 plus 1 is 95, right? So that was the reasoning. So here I'm asking you for another reasoning. Okay, one person has got it. We don't know it. He's just raising his hand. We have to figure out if he has got it or not, but yeah. Okay, maybe tell me what is an answer? Okay, so tell me the logic.
The previous number squared minus 5.
Okay, excellent. He's saying the previous number squared minus 5. 3 squared minus 5 is 4, 4 squared is 16, minus 5 is 11, 11 squared is 121, minus 5 is 116, 116 squared minus 5 is something that is left as an exercise, right? So I don't know myself. So, but yeah, so that is one way to answer this. Now, some interesting phenomenon has happened here, right? So it's not about these numbers or anything, but something interesting has happened. At least let's forget this thing, this second thing, right? So this is a slightly complicated series, but in the first series, something very interesting and fundamental about AI and ML has happened. Let's see what that is, right? So I'm going to think of it this way. So I have an input 2, and then it goes into a box, the green box, and out comes 5. And then there is 5, and there is a box, it's the same box that it goes into, and out comes 11, and so on and so forth. And now I'm asking, well, if I input 47 into this box, what is the output that I get? Now, most of you somehow figured out what is this box doing. And what did you say? Well, what did you say? So this is the input, this is the output, which is what I have given you. And I'm asking you, what is this in-between thing sitting in between? And you figured out that this box has this property. Okay, so I don't know why. Okay, so this can be moved. So this box is just doing this. As he pointed out, and what you said is also equivalent to this, is that if I give an input n, then it's going to do 2n plus 1. That's what it's going to return. Right? So what you did just now is a very hard thing for a computer in general. Now I'm going to ask you, let's say, did you figure out it's 2n plus 1? Okay. How did you figure that out?
I just checked the difference in between and multiplied by 2 and added it to the number.
But why did you want to do that? Yeah, you have to find the answer, but what triggered in your brain to think that this is the way you should approach this problem? You see what I'm getting at? Right? So it seemed very obvious to us that when I look at these numbers, immediately some of you put your hands up and said, well, it's 95, right? But because there is some internal processing that has happened, which we don't know what, which we are unable to say how. But still we know that, well, if I look at these numbers, somehow I have to multiply this by 2 and add 1 and I'll get the next number. We can't explain why we did that, but we did do that. Now, if we want a computer to do this, well, we must first know how did we arrive at this way to do this, right? So we ourselves are unable to explain how did we crack this problem, right? So again, this is a slightly harder thing. I mean, not really harder, but it takes some more time. I mean, all of you would have figured out if you had spent enough time on this, but somehow we figured that out as well, right? But if you had to teach a computer to think like you, first we need to know how are we thinking ourselves, right? So that itself is unclear. Somehow we got the answer. Now if you want a computer to do this, how do we get it to do that, right? So that's the thing, and this is the basic difference between, what is learning and what is not learning. Okay, I don't know. So in the first case, when we were looking at prime numbers, you were given a program and an input, and then I asked you, well, if the input is 10, what would be the output? If the input is 23, what would be the output? And all of you said, in the first case it's true, in the second case it's false, right? So we were given an input and a program, and then an output is produced, right? So we know what the program is doing. We know that we want to write a program to figure out if a number is prime or not. And given an input, you'll just run through this program, and then out comes the output. Easy, right? Whereas, in the second case, it's a much more interesting case, where I gave you the input and the output. In this case, think of it as 2, the input is 2, the output is 5, input is 5, output is 11, and so on and so forth. And I'm asking you to figure out what is the program. And all of you did that. This is easy for computers to simulate, right? So because if I give the program to the computer and an input, program is just a sequence of instructions, the computer can parse the instructions as told and then produce an output. That's very easy for a computer to do, because that's what computer is meant to do, right? So it will execute a sequence of instructions. Whereas in this case, some human ability has, come into picture, which is this green box here. You figured out the green box. And now we want the computer to figure out what this green box is. By just giving the input and output, we want the computer to spit out a program, which now if I give a new input, will also give me an output. Right? So you see the difference between these two setups? So the first setup is not learning. Right? So when we want to understand what is learning, now let's define learning a little bit more carefully. The first setup is not learning, whereas the second setup is what we are going to call as learning. So now how would you describe learning? From this understanding, what do you think is learning? Pattern recognition, right? So, and what are you recognizing the patterns from? Given set of numbers, in this case, given some input and output, we want to find some mapping that maps the input to the output automatically, right? So we want a computer to do that for us, right? So, which means that we want the computer to learn how to map this input to output, right? So that's a much more challenging task. It comes so naturally for us by looking at these numbers that it's 2 into n plus 1. But how do we make a computer do that is a tricky question to ask, right? So, and that's where the whole of AI and learning comes into picture, and we'll talk a bit more about this. Any questions so far? Okay. This is a question you probably should be asking, why should we care about this, right? So, I mean, if I want to know what to do, if I want to find out prime numbers, I'll write a program, you give me an input, I'll execute the program, out comes a number, right? So, that's how I'll figure out if a number is prime number or not. But why should I care about this new way of thinking about things where I give input and output and I ask computer to give me the program that maps a given input to output, which seems like counterintuitive in general, right? Why do you think that is? Why do you think we should care about this way of doing things, right? So the second way that I mentioned here, right? So where you give input and output and then you want to produce a program, as opposed to giving input and program and then producing an output. Why should we care about this? What are your thoughts?
Everything has a pattern, and to find the pattern out, we need to have a learning basis.
When you mean everything, what is everything? Give me an example of everything.
Like if you have to find the circumference and diameter of a wheel, then if you give the circumference and if you have pi, you can find the diameter.
So can't you write a program to do that? It's just a equation, right? So
We learned that, but if we have to do something else, then for example, finding the next 100 digits of pi, and we give a few random numbers for the computer to figure out, then it has to figure out.
what do you mean if you give few random numbers to a computer? What does that mean? So I want to make a distinction between knowing what to do, which is, I want to find out the area of a circle given the radius. That's just a program that I can write. You input r, pi r squared, out comes the output. I know what to do there, right? As opposed to saying, I'm not giving you the program itself, I'm just giving you the inputs and output, and then I'm asking you to figure out how to map the input output. For instance, I might say that if the radius is 1, then the area is pi. If the radius is 2, then the area is 4 pi. I only give you that information, and now if I ask you, if I give you the radius as 6, can you tell me what is the area of the circle? Right? So if you did not know that pi r square is the area of the circle, because a computer doesn't know what pi r square is the area of a circle, can we make the computer automatically figure out that pi r square is indeed the area of a circle, right? But what are we giving as input and output to the computer? Well, we are telling you if I input 1, the output is pi. If I input 2, the output is 4 pi, and so on and so forth. If I give a lot of inputs and then I'm asking computer to automatically figure out, what is the equation that, maps radius to an area of a circle. That's the difference, right? So, and why should we care about this? We care about this simply because science works that way, right? So nobody told us that pi r square is the area of the circle. We figured that out. Nobody told us that E equals mc squared. We figured that out, right? So all the laws, all the physical laws in the universe, we figured that out. But how did we figure that out? It's not like somebody got up in the morning and said that, hey, this is how the world works. No, right? So science works by observations, right? So we collect information and then we figure out laws based on the information that we collect, right? So I mean, your textbook might tell you that, hey, this is the circumference of a prism, right? So, but then, there has been a lot of thought that went through before we figured that out, right? So, or especially in physics, right? So, all of physics is experimental, right? So, you collect data and then you see what law best fits the data, right? So, that's how you figure things out. Right, so I like to think of it as these 4 steps which are fundamental to any science and also to machine learning here. Right? So first you observe things, you observe data, whatever data that can be, and we'll see some examples later. You observe some data. In this case, the data that we observed is 2, 5, 11, 23, 47. That's the data we observed. And then we hypothesize that there is some relationship between the first number and the second number. We don't know how the human brain did that, but to make a computer do it, we say that, well, there is some constant times n plus another constant b that will take me from the first number to the second number. I don't know what these constants are, right? So, but I'm hypothesizing that there is some linear relationship between the input and the output, right? So, if I take 2 multiplied by something and add something to it, I'll get 5, right? So, that's how you probably thought, right? So, I mean, what should I multiply 2 by and then add so that I can get the next? And then I'll see if it fits the next sequence also. If it keeps on fitting, and then I'm convinced that, well, that is the way things work in this particular example, right? So, we hypothesize, right? So, we think that this is how the world functions, right? So, we hypothesize that to go from the first number to the second number, you have to do some multiplication of the first number by some constant and then add something to it. Once you do that, then you figure out what these constants are. That your data will help you figure out, right? So your data will tell you, now from this data you can figure out it's 2 and 1. So it is 2n plus 1 is what maps the first number to the second number. So how would you do this, right? So we will talk a bit more about this for a second before we go to the next point. But if I know that the first number and the second number are related as some an plus b, how do you think I can figure out a and b from this sequence? How would I do that? So how did I conclude that A is 2 and B is 1 here? Trial and error? So how many would you have tried before you conclude this?
So you can observe it, right? Because the third number is 11, the fourth number is 23, and next is 47. So
Absolutely. That's because we are human. Now we want a computer to do this, right? So how would you mechanistically do this? Yeah, it's obvious to us, right? So, I mean, you might be asking, why is he even talking about this? Isn't this so obvious, right? But the challenge is to make a computer which is so dumb to understand something that is so obvious to us, right? So, that's where the trick is, right? So, how will you figure out A is 2 and B is 1 in this case? If you know that the first number and the second number are related as an plus b.
We could substitute fn and n into the equation and have it solve new equations.
Absolutely, right? So this is just a set of equations that you can solve. So you will do 2n plus 1 equals, an, 2a plus b is 5, 5a plus b is 11. That's enough for you, right? So in fact, you don't even need the other ones here. If you know that this is how the first number and the second number are related, you just need 2 equations to solve for 2 variables. I'm sure all of you have gone through equation solving, right? So this is like, there are 2 unknowns, a and b, and you just need 2 equations to solve these 2 unknowns, and it's pretty easy, right? So you just need 2, 5 and 11, and then you already know what is a and what is b, right? So that's how you can now make a computer do this, right? So because that's a principled way. You're actually telling me how to go about doing this to find out a and b. So that is equation solving, and then you can make computers solve equations. So let's not worry about how we can make computers solve equations. Let's assume that there are methods to do that. Now, what is the goal? What is the benefit of doing this? Well, the benefit of doing this is once you know a and b, you have the superpower to predict any next number given any number, right? So if I give you 103, and now you can say 2 into 103 plus 1 is the next number, which is 204, 207 in this case, or any number for that matter, right? So it's nothing to do with only 47 because you have figured out the general relation here, right? So this is what I'll call as OHLG in this case: observe, hypothesize, learn, and generalize. The learn is in italics because I still have to tell you what does it mean to learn. Right now it looks like equation solving, but we'll talk a bit more about learning as we'll see more examples. So let me pause here. Any questions at this point? Is this clear so far, what we are talking about? Okay.
Excuse me, sir. So just want to tell you, all these students have completed 3 weeks of CT.
Okay.
So with that background, they are sitting here.
Yes, I know that. Yeah. So, yes. So, which means that this should all be easy. Okay. Okay. So let's do something slightly different, right? So, let's say I want to do this experiment here with all of you, only the students, let's say, and I collect your height and weight. Okay. Your height in kilograms and your weight in, let's say, height in centimeters and weight in kgs. And what I want to do is I want to plot that here, which means that, let's say I'm going to be somewhere here, right? So my height is like 182 centimeters or something like that. My weight I won't tell you, but it's going to be somewhere, right? So somewhere here in this region. So each one of you becomes a point in this two-dimensional graph, right? So in this XY plane. Now if I collect, maybe there are 80 of you, if I collect each one of your height and weight and then throw points on this plane, how is that going to look like? How do you think the points will be? Where do you think the points will be? Yeah? It will be randomly scattered. Okay, I will come to that. Any other thoughts?
Be like a hyperbola.
It will be like a hyperbola. Okay, that's nowhere close to random. Yeah.
It should be clustered around some. For example, it should be clustered for the males and it should be clustered for the females because in our age group, I think we have a set amount of set height and set weight we usually average around. So it should be usually clustered.
Okay, so I got 3 answers. Any more answers? So one answer is random. So let's think about that, right? So when you say random, I'm assuming that it's kind of all over the place, right? So for example, if I fix, let's say the height as 120 centimeters, now if it is random, then I should have an equal spread of weight in this region, because I have no reason to believe that it is somewhere in specific region here. It can be everywhere, right? So which means that the points are everywhere. But do you expect that in this class, right? So do you think somebody who is, let's say, 130, 140 centimeters, and there are so many people with 130, 140 centimeters height, but then with different weights, is that can happen, but do you think that's likely here? Perhaps not. Perhaps not, right? Now, somebody said hyperbola, right? Why?
Because I've seen people who are tall but have less weight,
Ah.
and those people who are short and have more weight.
Okay.
People who are just equally medium tall and have normal weight.
Yeah, so we have seen all sorts of people. That's true, right? So, but do we have all sorts of people here is the question. You are right. So somebody who is short could be heavy. Somebody who is tall could be light. All sorts of people, everything is possible. That's genetics, that's how your parents are, how your grandparents are, what you ate this morning. All of this put together will decide your weight somehow, right? So there's so much biological process that has happened over millions of years that will determine what your height is, right? So, and your weight is such a fluctuating thing. But is that likely, right? So in the way that the world works, is it likely, is the question, right? So let me ask it slightly differently, right? So if I increase the height, what do you think will happen to the weight on an average for an individual? Yeah? It will decrease or increase? There will be slight increase, right? So you are expecting a taller person. I'm carefully using the words expecting because I cannot say that taller, if there are 2 people, one is taller than the other, that means that the one is heavier than the other. I'm not saying that. But on an average, you would expect from your knowledge of the world, from what you've seen so far in the world, that as height increases, typically weight tends to increase. There is a proportionality relationship between height and weight that you would expect. I'm not saying it will happen, right? So which means that if I plot this, I might get something like this. I'm not saying this is what it will be if I collect data from here, but it might be something like this, right? So as I increase the height, the weight might increase. Of course, there might be specific differences between different sets of populations, as he mentioned, between male and female maybe, and so on and so forth. We are just ignoring that for the moment and saying the main thing to notice here is that as the height increases, the weight tends to increase. So you will get, some kind of a curve, some kind of a spread like this. Of course, there might be somebody here, there might be somebody here, all that can happen, but this is average behavior that I'm talking about. Now the interesting question is, now there is one friend of yours, let's say it's me, and I'm very, very particular about not revealing my weight to anybody, right? I'm okay to reveal my height to you, but I'm very, very protective about my weight. But you as a data scientist, as a machine learning expert, really want to know what my weight is, right? So now the question is, you already have this data about people in this room, and maybe there is one friend of yours who says, well, this is my height, but I won't reveal you what my weight is. Now, can you think of a way to figure out the weight of this person? Yeah.
You can go with the correlation.
What does go with the correlation mean?
Means seeing a general trend with points laid out on them.
Okay. Any other answers? Yeah.
There is already existing data, and it won't be hard to find someone of your height. So if I look at the graph and see someone of that height, a point or few points in that range, I can probably guess your weight around that.
Okay. So you're saying, I don't care about this person, I don't care about this person because I want to figure out the height of this person. So I'll just look at this region and probably make a guess based on that. Okay, fair enough.
So we can find the
Average weight of the entire set of people?
only the weight of the particular set.
So this is my height. So what do you want to average over?
If there are many students with the same height, we can find the average.
But that's unlikely, no? So let's say, what's your height? 160 centimeters maybe? Okay. Let's say 162 centimeters, right? So now it's unlikely that there are going to be many with exactly 162. There may be 161, 160 and so on, but it's going to be hard to find out somebody with the exact same height. That's the problem that we have, right? So it's not like, of course, if there is many people with the same thing, what you're saying makes perfect sense, right? So you can just think of you as an average of people with the same height and then average their height and predict your weight. Yeah, but that may not happen. Yeah.
So we can find the average BMI over the chart and we can.
Average what?
BMI.
Average BMI. Okay. So you do the BMI calculation for each of these people. Okay.
And we can find the average of it and we can find the weight.
How?
We have to find the BMIs and take average.
Let's say the BMI is 22.
So we can height by weight squared.
Height by weight squared.
So we can find the weight.
Okay. But why is that a good idea?
Because.
So okay. So the question is, this guy's BMI might be something else. This guy's BMI might be something else, and
That's why you are taking the average.
That's why.
We are taking the average.
Okay, I see. Fair enough. Okay. Yeah.
First we'll take a particular range, 160 to 170, and then average the weight of.
Okay. So which is slightly extending on what she is saying. You may not get the exact number, but you may want to do something else. Okay. Fair enough. Any other answers? Yeah. You have an answer? Okay. Yeah. Any other answers? Before I tell you one method, which may or may not be a good method. Okay, so what I want you to do is go back to this principle that we have here, right? So we observed some data, and we want to hypothesize some relationship between height and weight, and now we want to learn from that relationship and then make a prediction for a new person, right? So that's what we want to do. So we have this data, and now we want to hypothesize some relationship between height and weight. And it appears that in this picture, we all agreed that as height increases, the weight typically increases. So what might be a good way to hypothesize that relation? At least by looking at the picture here, what might be a what might be a trend here? Right, so if I had to summarize these data points using a trend, using a curve, what curve would that be? It's an upwards positive sloped line perhaps, right? Now, which means that, here is a line. If I think this is the line that I want to use, the blue line is the line that I want to use to predict my weight for the height, then I would predict this as my weight, because once I have this line, then given the new height, I can make this prediction. Where is that? What is the corresponding value on the line for the given height? That would be my weight. So here is one line, right? But this is not the only line, right? So there are infinite possible lines. Here is another line. So if I choose the pink line, or whatever color this is, purple, pink, looks like pink to me. So then for this height, I would predict that as the weight. If I use the green line, I'll predict something else. Which line should I use? So how many of you think it's blue? How many of you think it's pink? Okay. How many of you think it's green? Okay, good. All of you are thinking. That's nice. So why? But why is it green? What's so special about green? I like pink. Most of you are wearing blues. What's so special about green? Yeah. Sit down. The points are scattered around the green line. Okay. What can you make that slightly precise? What do you mean by that?
It's more representative of all the points.
Okay. It's more representative of all the points. That's a nice word. I like that word. So we'll come to that. Yeah. Somebody else? You said something.
All of the points are gathered more closer to the green line than other lines. So more data is being perceived from the green line. So it is we can find a better guess of what would be a weight if we take the green line than if we take the other two.
Yeah, so I think similar to what you are also saying. He's saying representative, you are saying there is some notion of closeness that you can represent, right? So, which means that, so what does this tell us? Now, again, we'll go back to that OHLG thing. We observed the data, we hypothesize that there is a line that connects the height and weight, right? So, which means that if I give you a height, there is some magical line that is going to give me the weight. I want to figure out what that line is. And I'm saying, well, among these lines, somehow the green line is better, which means that for every line, I need to tell you how good is this line with respect to the data that I've seen, right? So the data is just the gray points, right? So if I can somehow come up with a measure that tells me for this data and given a line, this is how well this line represents this data, then among all possible lines, I can find that line that best represents the data, right? So that's the idea, right? So we won't really bother about how to figure that out in this talk now. But all of you got the idea that somehow it best represents, or the data is more scattered around the green line. Naturally, there is some, because all of you put your hands up for the green line, there is some valid way you are thinking about why the green line is better than other lines, right? So again, let's quickly summarize this idea here. So we observe the height and weight of students. We hypothesize that height and weight are linearly related, that there is some magic line. And then we find the best line according to whatever measure that we think is valid to understand, given a line and a data, how well this line fits the data. And finally, we want to generalize it to figure out what your friend's weight is, given his or her height. Okay. So this is almost same as what we did earlier. It's the same 4 steps: observe, hypothesize, learn and generalize, with a small change. In the first case, when I gave an input and output pair, it's still the input-output pairs that I give you. In the first case, it's n and 2n plus 1 always. If the input is n, the output is always 2n and 2n plus 1, and then you figured out automatically, well, what is the relation? Here, remember, there is no single line that passes through more than 2 points. Of course, between 2 points, any 2 points you can draw a line. But then if I take any 3 points, perhaps there is no single line that passes through all 3 points. Still, our understanding of how world works tells us that there should be a line that relates height and weight, and we are trying to figure that out, which means that the input-output is not really related using a line, right? So the difference is, in the first case, the input and output is exactly related using a line. I can think of this also as a line, right? So this is y equals mx plus c, where m is 2 and c is 1, right? So 2n plus 1 is also a line. It's a linear relationship. Whereas here, the input and output is, well, I have a height, and then the corresponding thing is that there is some magic line, but then I'm not giving you the height, weight of the exactly on the magic line, but then there is some noise added to it, some corrupted version of it. That's why you see this scatter. And why is that corruption happening? That's because of so many reasons, right? So that's because of, you know, how tall your parents are, and, you know, what was your cultural background, you know, what did you eat in the morning. All these things contribute to this noise, which we have no control over, right? So that small difference between, you know, away from the line is something that we have no control over. But still, we think that, you know, we are going to ignore that as noise. We don't want to care to model that. We only want to figure out what the line is, right? So that's the difference between these two things. And this is a much more relevant thing in science. You almost always get noisy data. You do experiments in your chemistry labs, right? So I'm sure when you do these experiments, it never goes well. Burettes and pipettes, I mean, that gives me nightmares already, right? So I'll never get the exact value, right? So, or even if you're doing physics readings, it's always going to be slightly off, right? So there's always going to be some noise, and this noise can be for multiple reasons. Maybe there is a parallax error, maybe there is a broken instrument. All sorts of things contribute to noise, but still we are saying that, you know, we'll figure out the line here, right? So that's the learning part, right? So we're learning a line. Now I'm calling this learning, not just equation solving, because you are learning it, you know, modulo the noise here. That's the important thing to keep in mind. Let me pause here. Any questions so far? Karthik, what's the time? 11. Okay. Take another 10 minutes maybe. Yeah. Questions so far? Okay. Cool. So why is this relevant, you might ask, right? Height and weight. Why should I care about finding the weight of a person given the height? Well, it has astronomical relevance, right? So this is back in 1801, I think, right? So when this is Gauss, and I'm sure all of you have seen that bell curve, right? So which is called the Gaussian distribution. How many of you have seen the bell curve? No? It's okay, fine. So this is a famous scientist who did exactly what we did, slightly differently from what we did. I mean, figure out this line from height and weight. He didn't do that. What he did was, they were trying to figure out the location of a planet. It's called Ceres. The planet was called Ceres. People knew that planet was somewhere, but they were not able to pinpoint where it was, right? So, and then some astronomer sighted that planet on 3 different days in 1801, and then he noted down, you know, the location of that planet. And then what happened is the sun's glare kind of, you know, in the sun's glare, the planet vanished. I mean, you could not see it using a telescope. And you know, for the next 9 months or so, the planet was kind of lost from human sight at that point with that instruments. And now they were trying to figure out where will it appear again, right? So, and this was a big astronomical question of those days. And this scientist called Gauss, he used this data, and then the data was there for 40 days or something. I'm just showing 3 days data, and used exactly what we did, right? So to predict height from weight, he kind of used this data and then worked out some calculations to figure out a model. He did this observation. He hypothesized that planets travel in certain orbits. It's no longer lines. It's going to be some elliptical orbits in which planets travel. That's because of Kepler's equation and so on. And then he used that to figure out where will you observe this planet again and when. And with some error, 1 or 2 days, it exactly showed up in that place, right? So there are a lot of, I mean, it's the same idea where you have some data and then you make some hypothesis as to how this data is evolving, and then you use that to figure out, make some predictions, right? So like how we did for the height weight thing as well. So it has, you know, several relevance in science in general. A very down-to-earth example, more not astronomical, but more down-to-earth. We'll quickly do one example, and then we'll close for this session. Let's say, you know, here is a slightly different example, where, you know, let's say you run a bank, e-commerce person, commerce, right? So let's say you run a bank, and what happens is you have a lot of loan history of customers, right? So what you have is, you know, you have information about people who have taken loans from this bank, and you know whether they paid the loan back or not. That's the information that you have, right? So, and now what you want to figure out is if a new customer walks into the bank and now you are the manager and you want to say whether this person, if I grant this person a loan, will that person pay the loan back or not, right? So if the person, I mean, if your computer says, no, this person won't pay the loan back, then you're better not give the loan, right? So you have to be, you want to make sure of you are giving the loans to the right people. So let's call this person Hari. Any Haris here? No Hari here, okay. So that was, I just tried that name so that somebody will be here, but unlucky. Okay, so what happens is, so there is some past customer history that the bank has, which is the data, the observed data that the bank has, and now there is this new customer Hari who walks in, and then you want to write, use this data to spit out a program such that for the new customer you should be able to say whether that person should get the loan or not, right? So this is our goal. So we are going to think of our input output slightly differently in this example. The input is, let's say, you have John, Mary, Smith, and so on and so forth. It doesn't look like an Indian bank, but nevertheless it's okay. So you have their features or inputs: age, gender, education, salary, married, location, etc., etc. And then your output now, like, think of this as equivalent of the height information, and the weight information which you wanted to predict is now here the decision whether that person paid the loan back or not. Right? So that is this information. And now here is Hari, who's 28-year-old, has this BS in data science, let's say, and then, well, he earns $16,000 and he's not married, urban, and then you want to figure out if you should give the loan to this person or not. This is the goal, and let's make it slightly simpler. Okay, so let's not look at all features, but then only age, salary, and then I want to decide whether I should give the loan to this person or not, right? So here is age, here is salary, and now John and Mary got the loans, that's why they are in green. Smith didn't get the loan, that's why he's in red. And now here is Hari, for whom we need to figure out if we should give the loan or not. This is Hari's age, this is Hari's salary. Now, as a bank manager, would you grant a loan to this person or not?
Yes.
Why? Because you have a lot of money? Yeah.
He is of a lesser age and has more salary. So as he grows older, he has more capability of giving back.
Okay. Okay, so that's one reasoning. Any other reasoning for people who said yes? Yeah.
The range between John and Mary is where if we have other customers as well, they are able to pay back the loan. So
I see.
since Hari is within that range of people who are able to pay back the loans, we can provide them.
I see. So what if Hari was here? You would have said no?
No, but it's still not below where people are not able to pay back. Still near that range of trustable people.
Yeah. So look at the point where I'm pointing, right? So if Hari was here instead of here, would you have suggested a loan or no?
I was just suggesting yes.
But okay, so then this range thing, how does that work?
Like we suppose we have like 10, 15 more customers just like this.
Okay.
And we have their data as well.
Okay.
If he is within that range of people who have paid back their loans,
Understood.
then we can trust.
Understood. So you still want to figure out some range of age and salary within which is like what he said as well. Yeah. Okay. Anything else? Any other idea? Yeah. The commerce guy. Sorry.
You can see that from the graph, you can see Hari and John almost, you can assume that they fall into the same demographic.
Mm.
And since John and Hari are almost similar in age and almost similar in salary, looking at John's history of paying back loans, we can assume that Hari would pay back the loan.
Sure. So how? Okay. So that's you as a person looking at this picture and telling, right? So always think of how to make a computer do this, right? So how would you make a computer? What would be the program that will decide, right? So it's finally our lives are going to be decided by programs. So what program would decide whether Hari gets the loan or not?
You could set a particular benchmark, suppose let's say $12,000
Yeah.
and at a particular age, and that's a slope. You could set a slope of sort of line,
Okay.
and you could tell that to the computer. Anything that falls above, it's a yes. Anything
Okay.
that falls above.
Fair enough. So the other option is you kind of have a line and then anything that falls on one side is perhaps yes, the other side is no. Okay, fair enough. Any other answers? Second answer.
You can connect the points of all the points who have paid back the loan. Example, Mary and John.
Uh-huh.
If Hari is near the line, he will get the loan. If Hari is away from the line, he won't get it.
Well, if I draw a line connecting Mary and John, perhaps Smith will also fall on that line, no? So think of this line. So maybe Smith is slightly away from the line, but he's close enough to that line. Which line? The question is, what is that line? Right? So that will tell me Mary and John should get the loan, whereas Smith should not. Is it the line that joins Mary and John or something else? It's clearly not the line that joins Mary and John, right? So because that would perhaps pass through Smith or close to Smith as well. We'll come to that, yeah. Any other thoughts? Yeah.
So they have more details like assets and collateral.
So that brings an important point, right? So it's a good thing to have more details, but let's say I was a lousy bank, right? So I didn't store any of the asset details of previous customers. So we have to work with the data that is given to us, right? So we cannot demand more data, right? So maybe this happened 10 years back and now I cannot go back and ask what was Mary's assets and so on at that point. Yes, I take your point that if you have more data, you can do better prediction, but here I may not have that data, right? So, yeah.
We can take the data and we can say that if the salary is this much, like within this range, and if the age is this much, then if they have paid back the loans, then we can trust the person, and if they haven't.
Okay, cool. So that's similar to what was also mentioned, right? So any other answers? Okay, third answer from it. Okay.
Like barrier.
What is barrier?
You can say that at this age and at this salary, anything above or below them, they can pay. Anything below or above, they cannot.
Yeah, similar to what you're saying. Yeah, one more.
One doubt though. Are we giving the same amount of loan to every person or are the loan amounts different?
For the moment, assume it's the same amount. Let's say some basic loan that everybody wants to buy a self-driving car. Let's say it is for that. But yeah, so those things also will matter. Yeah. Sit down, sit. Yeah.
Without keeping the age and salary as count, we could identify a common bracket in which people who have paid back the loans,
Understood.
which are not typically based on a specific age and a salary given to them. For here, suppose Mary and John have paid back their loans. So anywhere around, they're not basically average.
Yep.
Maybe somewhere closer to that, and even not necessary that they are from a similar age group or have a similar salary. If they're around
Yeah. So you're basically somehow saying that, hey, Hari looks like John. Is that what you're saying? I mean, meaning Hari's credentials look like John's credentials. So he is close to somebody who got the loan, so he should also get the loan. Is that what you're suggesting?
kind of, but
Okay. That's fair enough too. Yeah. Okay, so I've gotten enough answers. So we'll see why all these answers are correct. In fact, I'll do some magic and then show you exactly the answers that you said now. Okay. So here is one answer which she said. So, your program could be the following. It can just say, you can decide output based on the label of the nearest neighbor, right? So which means that here is Hari and then John is the nearest. I mean, I don't have Hari's detail with me. There is nobody exactly like Hari who has walked into the bank before, but then there is somebody like Hari who is John, who is the closest, right? So if I have to pretend Hari as somebody that I already know, that would be John, and for John I gave the loan. I mean, John paid back the loan, so hopefully Hari will also, right? So that is one way to deal with this problem, which is what she mentioned. The other thing could be to come up with what is called as a decision tree, which some of you were saying that, I'll first check if the age is less than some amount. And then, yes, if the age is greater than 30, then immediately you don't get a loan. right? So that might be your answer, but then if the age is less than 30, then you may want to check what about the salary. If the salary is greater than $10,000, then maybe you will give the loan, and so on and so forth. Which means that the program that you are deriving out of this data is this tree, right? So this is like in computer science, this is called as a tree, and then you can now run your new information of Hari through this tree, and then figure out if the loan should be granted or not. This is also something some of you said, and the third would be something that I think answer came from there. You draw a line, right, with some slope, and then you say that, well, from this data, it looks like I can draw a line of something like this, and then everybody, not the line that joins Mary and John, by the way, a line that divides those who got the loan and those who did not get the loan, and then everybody on the left side gets the loan, everybody on the right side does not get the loan. Now, all these are valid things. We won't really talk about why is one better than the other now, but these are natural things that you already came up with. Now, when you thought of this, then somebody thought that, well, I should draw a line, and then the question is, that's the hypothesis that I'm making. There is a line that separates those who got the loan versus those who did not get the loan, and I have to figure out where to draw the line, right? So then, which means that I'll have to find the best line in that case. Here I have to find the best set of rules, right? So this is a rule. Is the age less than something? Is the salary less than something? That's a set bunch of rules that I want to figure out automatically from my data, so that with that rule, then I'll be able to figure out if a new person should get the loan or not, and so on and so forth. Here it's much simpler. I just look at who's the closest guy to me, and then based on his or her decision that the bank had already taken, I will make a choice. All these have advantages and disadvantages, which we won't talk about here. That's what you will perhaps learn if you are doing a course here, but all these, whatever you said intuitively, are all valid things, just that they have to be kind of trimmed a little bit more. Okay, let me pause here. Any questions at this point? Yeah. Quickly, so we'll talk a bit about other things, another 5 minutes, and then I'll stop. So far we have seen data which is given to us in a nice format, right? So the data is always given as age, salary, etc., height, weight, and so on and so forth, right? So some numbers were given to us, and then using that numbers, we were able to figure out whether somebody should be given a loan, somebody should not be given a loan, etc., etc. But data could come in arbitrary ways, right? So maybe this is your data, right? So people are writing numbers in, let's say, on a tablet, right? So let's say an iPad or something like that, right? So you might write 0 like this, somebody else might write 0 like this, I might write 0 like whatever, this Lord of the Rings kind of a thing. But as humans, we kind of recognize all these are zeros, right? So, but now you cannot write a rule that says, this is a 0, this is a 0, this is also a 0, right? So it's very hard for a computer to know from a rule-based way to figure out which of these are actually zeros and which of these are not zeros. Right? So now, this is what we'll call as unstructured data. Images are unstructured data, speech is unstructured data, text is unstructured data. These are all images. And now, computers can only work with numbers, not the numbers that I write, but then actual physical numbers, right? Zeros and ones, which you can convert numbers to. So if this is how, right? So these are photographs, let's say, of things that I've written on my iPad. Now, I want to figure out from this, if I show this is a 9. I want a computer to figure out. This is very easy for me, right? So I look at this and I say, hey, this is a 9. But it's a very hard thing for a computer to detect this as a 9, because 100 different people write 100 different ways the number 9, right? So the same thing, but then there are small stroke differences, small calligraphical differences that we'll have among ourselves, that it's very hard to tell a computer that what are these small differences, right? So it becomes very hard. So now, we have to convert these into numbers somehow. And what do you think is a good way to convert these into numbers so that the computer can work on these numbers to figure out, given an image like this, what is the number written on this image? How would you do that? If you had to think about that problem, how would you do that? Is the question clear? So my problem is, I have this data and I tell you this is 0, this is 0, this is 0. I have all this data. Just that I don't have, let's say, the last corner one, right? So, and I want the computer to figure out, given this input, automatically figure out this is 5. How can we do this? So there are no nice numbers as features, right? Height, weight, age, salary. It's not like that. It's an image, right? So how can you convert an image into numbers?
So we have the data in the form of images. We can take one specific benchmark such that like this is the number 0. And so if the image that we've given is very close to the
What is close? That is what I'm asking. How do you measure closeness of images?
like if it looks almost exactly
How? How can you make computer do that? I mean, of course we can do that. That's why these things are easy for us. That's why your captchas are a thing, right? So because it's easy for humans to recognize numbers even if they are very, very squiggly, but then it's very hard for computer to recognize them. So you cannot do a robot that can automatically crack captchas, but then humans can still do that, right? So our eye is very evolved, but the computer is not so evolved to break a captcha. That's why captchas are useful, right? So now we want the computers to make this work. Yeah, but I understand, right? So you have to somehow make the computer to figure out closeness of images, which means that you need to represent images in some way, right? And one way to represent, well, this is which is what I call as features or the input, right? So the input is not this. This is a useless input to the computer. This has to be converted into a bunch of numbers, right? So and how do we do that? What's the most natural thing? How are images stored in a computer, by the way?
From pixels to binary.
Pixels to binary, right? So so basically a computer is going to not see this 3, it's going to see this as a bunch of numbers. This is a very simplified thing where this is just black and white or grayscale, where wherever there is white, it's 0, wherever there is black, it will be 255, and closer to black, larger the number, right? So we can still kind of think of this as a 3, right? So, but then these are a bunch of numbers that the computer thinks is corresponding to this, right? So you can think of these as my features, like age, salary, height, and weight. This is the set of numbers that represent this image, right? So now you have to use these numbers to make predictions for new things, right? So so basically this is another typical challenging thing that happens. So the overall pipeline, right? So and I'll probably stop with this, is that you still want to observe, collect data. If the data is unstructured, you have to use an intelligent way to convert that into features. Pixels is one way, but then there are more sophisticated ways. And now then you learn a program from the input and output that you have. And that program will mean that you are hypothesizing this is the way input and output are connected, and then you learn something from that. And now you predict for unseen data from the program that you have figured out from data, right? So, well, sometimes these feature conversion happens automatically, and that's, if you've heard of deep learning, that's a term that you may have heard. So where this feature, the computer automatically figures out what are interesting numbers to use to represent images, and then it will use those to learn these hypotheses as well. We won't get into that here, but yeah, I just wanted to make a note of that. So there are several examples. We won't really talk about details, but then there are several real world examples where machine learning can be used. You want to detect, given an email, whether it is spam or not, you have to collect a lot of emails, say some emails are spam, some emails are not spam, and then represent text as some features, and then again learn a hypothesis. It's the same idea again and again. Observe data, hypothesize the connection between input to output, learn from data, and then predict, right? So I'm sure many of you are using Gmail, and Gmail has a spam classifier, right? Sometimes your mails automatically go into the spam classifier. How does that happen, right? So you didn't tell the mail to go to spam classifier, it automatically goes, which means that Google has had a lot of emails which it thinks are spam, which it thinks are not spam, and then it automatically figures out, given a new email, whether it should put it in your inbox or in your spam box, right? So there is some line that Google has drawn, and then if the email falls on one side of the line, it will go into the spam box, and the other side will go to the non-spam box, and so on and so forth. That's one example. And you can use machine learning for a lot of things. You can use it to forecast things, forecast rainfall. Will it rain tomorrow? How much will it rain? Or to recommend movies based on what type of movies you watched. Can you recommend what movies might be of interest to you? Movies will have some features. You can use the same thing there. Friend suggestions in your Instagram, Facebook, whatnot, social media, Snapchat, I don't know. All the latest social media that you use, which you're sure know better than me. There are other things as well. We'll kind of skip this for the moment in the interest of time. So I'm going to skip these things for the moment. So I'll kind of complete with answering this question of which we started with, what is learning? I mean, how do you learn to learn? To understand this, we first say that it's not a program, right? So you don't know what to do. It's not like a procedure that you already know to solve. Given an input and a program, we don't know the program. And you cannot simply memorize, right? So for example, different people draw 0 differently. I cannot memorize all ways of writing 0. And then if a new person writes 0, I cannot figure out if it's 0 or not, right? So because every 0 is different. Each of you write the word number 0 differently. So I cannot simply memorize. And of course, it's not magic, though you will see some kind of magic tricks in 5 minutes, but it's not really magic. It is data driven. So the key is you have input and output in the form of data. And what you do is you learn a hypothesis so that you can predict for future. Right? So that's the key thing, right? So the input and output is given to you, you get the program out of it. And if it's not magic, what is it? It's basic math. It's math that perhaps all of you are already seen, and some high level maths that you may want to see. And I won't really trouble you with what these maths are, but we want to understand lines well. Lines keep making an appearance in whatever I spoke. And the way to understand lines, the mathematical subject to learn lines, to understand lines better is called linear algebra. It's linear because there is a line in it already, right? So the algebra of lines is called linear algebra. So that becomes a very important subject for machine learning AI. Of course, there is always this noise. Things are uncertain and you have to deal with uncertainty. And the mathematical way to deal with uncertainty is the language of probability. So we would need probability a lot to understand machine learning, AI in general. And finally, you want to make a decision. You always want to choose the best line. You want to choose the highest profit, least loss, etc., etc. So the way to figure out what is best is using a technique called optimization, which boils down to basic calculus. How many of you have already seen calculus or gone through calculus course here? Okay, so okay, if not, you will eventually see calculus in your school. And remember that if you're interested in these kind of things, calculus becomes a very, very important thing as well, right? So basic calculus, but it becomes very important for optimization as well. Okay, so with that, I'm going to stop here. So we have 2 more parts to this talk. Actually 3 more. So this is the talk part of it, which is over. Now we will see a small demo. Karthik will help us with a small demo where you will see machine learning AI in live action for a small problem that he will explain. And after that, I will invite Vivek for a few minutes. Vivek is a student in the IITM BS program here, successful student in the program, and I just want him to give a few thoughts about what the program is, what you might get from the program. And then we'll open up to questions in general to the audience, right? But so far, with whatever we've seen, are there any questions? I'll take that first, if there are any. Is it kind of clear what we are talking about here? Okay, great. So now I'll invite Karthik for the demo.
So this is a demo that was prepared by Professor Arun's PhD student. So I'll just yeah, so is everyone able to see I hope it's visible, right? So, yeah. So, can anyone guess what is happening here? What's the program doing here? Okay, so it's identifying something, okay? So, it's identifying objects. So, do you also see a number that is out there? So, there are 2 things on top, right? So, can you read that? Okay, and there is some number there. What is that number? What do you think it is?
How close of a thing it is to that thing?
Okay, so Prof was discussing about this in the 2 slides back, right? Uncertainty, probability, right? So it's 90%, roughly 90% confident that this whatever it sees here is a person. Okay, so I'll take a few more objects. This is okay. So what does it say? Okay, sports ball, and how confident is it? Okay, so that is one. Few more examples. So let's see if it's able to recognize this. Okay, so you can see that it's kind of confused. So it's 50, 60% confident. But yeah, so that is a cell phone. We can.
Why do you think this confusion?
Yeah. So yeah, as a question. So I'll first ask that as a question. So why do you think it is confused about this particular object here?
Maybe switch on the screen.
Okay. So okay, I'll do that. But maybe it's slightly better, but still it's confused. 80%. So what could be the reasons for this confusion? Any guesses? Okay, so a cell phone is similar to what other kinds of objects? Okay, brick. What else? A remote control, for instance, right? So earlier in the lecture, what we saw was there is this input and output, right? So the machine is learning from a lot of input and it's trying to predict some output. So this specific problem is called object detection. Okay, so we are actually teaching a computer to recognize different kinds of objects, and the way we do it is by providing a lot of images, right? So images, again 2-3 slides back we saw images of handwritten digits, right? So instead of handwritten digits, what we provide to the computer here is lots of images of objects in real world. Okay, so we provide lots of images of balls, for instance, right? So we give the input as a ball, and we also give, what do you think the output should be if the input is a ball? So what do we expect the computer to learn? Is it okay to identify that it's a ball? Is that all?
Identify the structure of a ball.
Okay, that is okay.
Ball is round, so anything that's round should be.
Okay, so there are two things actually happening in this program. If you notice, what are the two things?
Identification.
And
And showing how close it is to the object.
okay, so where it is, right? So the pink color boxes that you see there, right? So these are called bounding boxes. Okay, so that is actually a problem of localization, right? So we are trying to localize in this window where that ball is, right? So see, this is again, I'll go back to what Sir mentioned, right? So this is a very, very simple problem for humans, right? We start learning this right from when we are kids, right? So parents typically start with this, right? So there's a ball, and so all that is second nature to us, but that is not the case with a computer. Okay, so it can be it is actually a really hard problem to solve, and so I'll just want to show you a couple of more instances which end up confusing the computer a little bit more. So this is a book. Okay, so interestingly it's performing very well now. So just before the talk, when we were testing it, it was confusing this with a laptop. So yeah, maybe I have two final examples, and with that so this is a mouse, and I have a toothbrush. Okay, so two more to go. So this is a toothbrush. Okay, again quite confident, and finally the mouse. So mouse, I think it certainly makes a mistake, and it calls it a cell phone. Okay, so and it is quite confident that it is a cell phone. Now, that's a bad thing, right? So these things happen. So when you actually train these algorithms, so what happens is there is a room for error. Okay, in fact there's a big room for error, and earlier in the talk we were talking about self-driving cars, right? So it's a very good application of self-driving cars. So you actually need object detectors to understand what is there in front of you. So you need to, even before navigation, detection is a very important problem. You need to identify traffic signals, you need to know when to stop, right? So if the system identifies a man as a pole or something, things can be really bad, right? So these are currently what many data scientists are working on. Okay, so all these are exciting stuff which you will learn as you go along in the program. Yeah, so once again, thanks to Professor Arun's student for giving us this demo. Okay, so